Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In the early 1990s, the rise of active vibration control motivated researchers to develop active noise control approaches. In this video, we'll learn about the techniques of active noise control, their challenges, and their intrinsic limitations.
So let's get started. We as engineers would only resort to receiver-based noise control when the success of noise control by the source or the path is limited. And at the receiver, we can use passive and active methods to limit noise exposures. The passive method would be simply to block the wave passage to the ear canal, for instance, using earplugs or earmuffs. The active approach is to send additional signals into the environment that have a same amplitude but opposite phase of the noise to help cancel this environmental sound. The premise for active noise control is therefore to cancel out undesirable sounds at the receiver. Take, for instance, this noise in the environment. It sends signals to, for instance, our error sensor, this microphone. We wish to cancel the noise at this microphone location and nominally elsewhere. To do that, we introduce a control source that sends a signal determined through algorithms that cancel the noise at the microphone. And we see great success here, a large reduction from before to after. On the other hand, by using an additional microphone in the environment, we find that the net sound in the environment is actually greater with the control source than without, except at the location of the error sensor. This is a fundamental challenge of active noise control approaches. So what is the fundamental construct of an active noise control algorithm? Well, the noise prevents us from achieving the target sound field, what we want to hear. So, we wish to find an optimal finite impulse response, or FIR, filter that we can convolve the noise with to remove the error. So here, for instance, we know the noise, we have a good reference measurement of it through our error sensor, and this is fed into the FIR filter, convolved, and then added up with what we actually hear to remove the error and recover what we want to hear. Now, this is purely computational as shown here. To actually implement it, we need to learn from our mistakes. So the error is fed back and automatically updating the FIR filter through an LMS, or least means squares, algorithm. In practice, this requires actuators, a control source, and this has its own path and impulse response to be contended with. So in practice, the XLMS algorithm is adaptively updated to model the actuator path and then feed this signal back into what we want to hear. When added with the noise, that canceling signal identified through the filtered XLMS algorithm succeeds to reduce the noise level and indicates that what we hear is what we want to hear. But there are a number of intrinsic challenges to achieving active noise control, especially with global noise attenuation. The control source arrangement needs to be very similar to the noise source size and location. Ideally, we want our control source to be located coincident with the noise and be of exactly the same size. There also must be high coherence between the reference noise measurement and the error signal. We need some indicator of what the noise is before it reaches the listener. For instance, it might be an accelerometer on the rotorcraft hub. That frequency of vibration will be very coherent with the noise that's propagated into the cabin. The error signal location must also be chosen to be aware from where the noise arrives. We don't have an error signal right next to the rotorcraft hub. Otherwise, our control sources will likely pump too much canceling audio into the environment, leading to very good noise cancellation at that error signal, but very poor noise cancellation elsewhere, and in fact, an increase of sound level elsewhere. Finally, if we use multiple error signals, in other words, multiple microphones, randomly placing those microphones will lead to better success in global noise attenuation. But even if we follow these principles, there are still intrinsic limitations on noise attenuation through active noise control approaches. The first and foremost one is practical. For frequencies 3,430 Hz and up, the wavelengths are less than 10 centimeters. Now recalling that the distance from ear to ear is approximately 180 centimeters for the average human head. And that's the measurement from the eardrum on the left ear to the eardrum in the right ear. So if a person moves their head by 1 centimeter, the effectiveness of that noise control approach would be reduced dramatically for these mid to high frequencies. Very often, as a result, best noise control is achieved for frequencies of about 500 Hz and less. We also need very good reference signals of the noise, and these are not often always available. For instance, turbulent airflow out of ducts in vehicles, or chassis vibration as we travel over rough road terrain. These all produce noise in the cabin, but they are stochastic, and it's very difficult to identify a good reference signal to use in an active noise control algorithm. Fortunately, there are a number of new innovations that are happening that help us achieve greater performance of active noise control despite inherent limitations and challenges, one of which is to use acoustic energy density sensors. Acoustic energy density is more or less constant in a closed space, for instance in a closed vehicle cabin or in a closed room. This means that an acoustic energy density sensor is a good indicator of global sound levels in the space. This has been recently used for much better active noise control results. The parametric acoustic array is one emerging technology that creates very directional beams of sound by modulating ultrasound with a sonic frequency. These beam-like patterns can then be used in active noise control approaches, so that rather than increasing the net audio in the environment, the active noise control effect is achieved where we want it without this spillover phenomena. To summarize what we've learned, active noise control cancels unwanted sounds on the basis of adaptively reducing error signals to zero. Headset-based active noise control is most effective since the noise and control sources follow the error sensors, which are in that case the person's ears. But there are fundamental limitations to active noise control that prevent its widespread implementation, despite great enthusiasm for many years for the very principle itself. Fortunately, recent advances in error sensors and control sources offer new potential for free field ANC applications.
That's it for this video. In active noise control, the computing power is one of the governing factors of success. In the next video, we'll learn about audio compression techniques, which helps us best utilize computing power and bandwidth for our acoustics applications.